I am Kamaleswaran from EEE department. I am here to explain the OLED limitations in depth of technical overview. The burn-in and image retention. The permanent burn-in, the static image displayed over a long periods permanently damage the organic pixels, leaving the ghost image. Even the screen shows the different content. The uneven degradation. The individual RGB subpixels degrades at their different rates. The blue OLEDs have the shorter lifespan than the red and green, causing the color imbalance over a time. Temporary retention. Short-term retention can occur after displaying the same element, example a status bar, and may fade after a few minutes of a variety content. The HUDs and the static UI risk. The navigation bars, channel locks, and game events are especially at high brightness for an extended durations. The lifespan and organic degradation. The OLEDs approximately give the 13,000K of lifespan. Comparatively, the LCD have the 16,000 hours of lifespan. The brightness drop by 50%. The blue fastly fade. Why OLEDs age faster? The OLED pixels are the organic compounds that chemically degrade with the use and time. Unlike the inorganic LEDs and LCD backlights, the OLED emitters irreversibly lose the efficiency. The high ambient temperature, prolonged the high brightness usage, and moisture all accelerate this process. Brightness management and critical longevity. The high cost and manufacturing challenge. Why OLEDs are expensive? Complex vacuum deposition and encapsulation process, low manufacturing yield and compared to LCD production. Expensive organic emitter material, specialized equipment required for large panels. The WOLED plus color filter approach that adds layers and cost. Water sensitivity and durability. Moisture instruction. The organic compounds reacts instantly with water vapor. Even a trace moisture causes dark spots and a catastrophic pixel failure, requiring the hermetic sealing layer. Thin and fragile structure. The OLED panels are extremely thin and pressure to damage. The flexible OLED variants requires the robust protective layer to prevent the cracking. The heat sensitivity. Elevate temperature above the 85 degrees Celsius accelerates the organic degradation significantly. Outdoor and automotive OLED designs faces the major terminal management challenges. Encapsulation and complexity. The multiple layers encapsulation of glass, metal foils, thin film, the complexity costs are very high. The any pinhole effect dealing leads to the failure. The brightness and PWM flickering and power draw. The peak and sustained. The OLED achieves the very high peak brightness 1000 to 2000 nits for HDR. The sustainable full screen brightness is limited to 200 to 500 nits. The prolonged high brightness accelerates the pixel wear. The ABL, the auto brightness limiting kicks to protect the panel. The PWM flickering. It means the low frequency PWM below the 1 kHz causes the flicker sensitive notice, can trigger the headache, eye strain and discomfort. The DC dimming is preferred but harder to implement in OLEDs. High pressure PWM are greater than 2 kHz largely mitigates the issues. The dark content, the power consumption. The dark content is equal to very low power pixel off. Bright white UV consume the more than the LCD with the backlight. The dark mode on OLED saves the significant battery and mixes the content of average favorably versus LCD. Summary. Burn-in. Permanent pixel damage from static content. Lifespan organic delay limits the longevity. High cost. Expensive materials, complex and manufacturing. Moisture, extreme sensitivity to water and humidity. PWM flicker, low frequency dimming causes the eye strain. Brightness, sustained brightness lower than LCD. Despite their limitation, OLEDs remain the gold standard for contrast, color accuracy and thickness. Thank you.